Hello guys, this is Code and Code, and this is video editorial for the we are not video editorial but video lecture, and in this lecture we are going to study about the minimum number of moves required for a knight to move from one position to another on the chessboard. So again, let's go through the problem statement, but before that, I've already released a video in which I've talked how what are the things that we are going to cover in this week, and this is, I guess, the first lecture of that video. So there are, I guess, 10 or so, something like 10 or 12 lectures that I'll be covering in this week. So this is the first lecture for that. If you haven't seen that video, you can go and watch those that lecture. But before starting this lecture, since this approach uses BFS on 2D grid, I've already explained how we can apply graph algorithms like BFS or DFS in previous lectures. How you can apply BFS or DFS, these kinds of graph algorithms on 2D grid. I have already explained those in previous lectures, so make sure you have already watched those lectures. So the problem statement is you are given a chess, or basically 2D grid. It doesn't matter, it doesn't need to be a chess. It is a 2D grid of size n cross m. So there is a knight on position x comma y, and there is a target cell a cross a comma b, and we have to find the minimum number of steps for the knight to reach the target. So before that, before discussing the algorithm, if you must know the moves of a knight. If the knight is at this cell, then it can move to any 8 position which I represented using this blue pink color and the X. Now if a knight is at position at this cell, then it can go here, or it can go here, 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 and so on. There are 8 different possible moves for a knight from certain, at max 8, from certain cell xy to it can move to these 8 cells. Now these are the possible one moves for a knight. Now if you see, if the coordinate of the cell in which the knight is x comma y, then this cell would have coordinates x minus 2 comma y plus 1, and I'm not using normal 2D xy graph. This is the 2D array. So the row numbers start from here, and it goes from 0 to 0, 1, 2, and so on, increasingly from top to bottom. And similarly for y coordinate it goes from left to right, increasing from 0. So this cell is 0, 0. As you all remember, this is simply 2D grid. This is not a graph, a normal graph where x coordinate is this and y coordinate is this and so on. This is not like that. This is the x coordinate, or basically the row number, and this is the y coordinate, basically the column number. So if there is a knight in position xy, which is this cell, then this cell would have coordinates x minus 2 comma y plus 1. You can see in the row we are going up by 2, so row number would decrease by 2, and in the column we are increasing, we are going 1 towards right, so column number would increase by 1. So this cell would be x minus 2 y plus 1. Similarly the rest I have already shown, so you can confirm it. If there is some mistake, just mention it in the comment section. So these are the possible moves that a knight can have. Now if you remember, to apply BFS or DFS on 2D grid, we declared 2 direction arrays, change in x and change in y. That is why we have dx and dy. So in BFS or DFS, there are 2 different ways from one cell you can move to another. One way is you can move from one cell to another if they share a common side. So there are 4 possible ways: up, down, left, or right. Another way is you can move to all of those cells which either share a side or a corner. So in that case you have 8 different cells you can move from a current cell. So you can go here, 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 here. Also you can go here, 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 and here. So this is for normal BFS and DFS. For that we create two different direction arrays. For this, the direction array changes a little bit, and the direction array looks like this. I'm starting from here and going clockwise direction. So this cell from here to here, if you move from this cell to this cell, you are making a change in x by -2 and making a change in y by +1. So that is why -2 + 1. So for this cell we have created, for we have made an entry in our direction array. For this cell, change would be -1 plus 2, so -1 plus 2 plus 1 plus 2, so +1 plus 2 plus 2 plus 1 plus 2 plus 1, and so on. So this is how your direction array in this case would look like. When you are applying DFS or BFS on 2D grid, it all defining the direction array is most important. If you mess up with this, you mess up with algorithm. So make sure that you define direction array properly. After that, so how we are going to apply BFS? Of course, since we want to find the minimum number of steps from one position to another, so that is why we will be using BFS. When you want to count the minimum number of steps, you want to count the minimum number of distance, and so on, where each operation costs equally. So if you move from here to here, it costs one operation. You can move from here to here, it costs one operation. In some cases, like when you have a graph and the edges are this time weighted, so edges going from one cell to another may cost different from going from different to different cells. But when the edges are not weighted, so moving from cell 1 to 2 would cost 1 unit. Moving from 2 to some other node would also cost 1 unit. So in those cases, BFS is applicable. BFS is applicable in only those situations in which each operation costs equally. If the graph is weighted, then each operation, each move may cost differently depending upon the edge weight, right? So that is why when the graph is weighted, we cannot apply singles or shortest path using BFS, but we have to go for Dijkstra. Similarly, here we can apply BFS because each operation is going to cost us only one move. That is why we can apply here. So now we are going to apply BFS. And how BFS works? Of course, we have this is the original array, the input array you can call it. This is distance array. It would keep track of all of the nodes that we have discovered and their distances. So this is the source node, this is where the night is, and this is the target cell. So we have to count the minimum number of steps using which we can reach the night can reach from this cell to this cell. And you can see the answer is 2 because first of all, you can't reach this node in this cell in one move, of course, so it would be more than one. So you can reach there in 2 steps. You just go here and then from here you can go here. So answer is 2. Now we need to find the minimum number of steps. That is why we are going to apply BFS. And to apply BFS, we need some arrays like distance array to keep track of distance of each cell from the source cell. And since source itself is at distance 0, that is why I filled already the cell 2 is at distance 0 from the source cell, because this is the source cell. This is from where we have to start. This is the cell where night is. So now how BFS progresses? If you remember, you have a source cell, you insert it into the queue, initialize the distance to be 0, mark it as visited. This gray color represents visited. After that, algorithm starts. Remember, so what you do when algorithm starts, you take out the front element, so current element is 2 and you remove it from the queue. We have removed it from the queue. Now all of the nodes which can be traversed from here would have distance 1 greater than the distance of current node. So distance of current node is 0. So all of the nodes which are visible, all of the cells which are which you can visit from this node, this cell will have distance 1. So from this cell there are 4 cells you can visit. This and this. So these 4 cells you can visit. You can go to from the current position in one move. So you can either go here or here or here or here. So there are 4 cells which are reachable from current node in one move. So all of these will be inserted in the queue. And of course, all of these are at distance 1 from the source, because this itself is at distance 0 from source, and you can reach any of these cells in one move. So distance of this plus 1 would be the distance of these 4 nodes. So these 4 nodes, these 4 cells can be reached from source, which is this, in 1 unit time or 1 unit move. After that, everything is done for this current node. So all of the node will be marked as visited as well. Now the algorithm proceeds again. What we do, we take out the front element from the queue. So we have taken the front element from the queue and removed it from the queue as well. After that, this is 14 means this node or this cell. So from this cell, what are the moves you can make in one step? From this cell you can go to either here or here or here. You can't reach here because this is already visited, so that is why we can't make this move. You can't go from here to here again. So that is why only these 3 cells are reachable in one move from this source node, which is 14. So all of these 4 cells will be inserting into the queue, and also the distances of these 3 cells would be 2, because their source is at distance 1 from source node, which is this. So this cell is at distance 1, and now since these cells are reachable in one move from this, so whatever distance this is having plus 1 would be the distance of these 3 nodes. So this is having 1 distance, so all these 3 nodes will have distance 2. After that, the work of this is completed. So we will take the next front element from the queue, which is we will also mark them as visited, and that is represented by gray color. Now the node, then we will take the next from the queue, which is 3, 4, and also we will be removing it from the queue. This is the standard BFS procedure. If you see, we are following the standard BFS procedure. If you haven't seen the algorithms, the lectures on BFS, I highly recommend you to watch those lectures first, then come here, so that you can have a better understanding of what is going on. Now the current element is 3, 4. 3, 4 means this cell. We have covered this, and now it's time for this. From here, what are the cells you can visit in one move? These are the cells you can visit in one move. You can go here, you can go here, you can go here. You can't go here because it is already visited, so we won't consider this. Otherwise there will be an infinite loop. This will be adding this into the queue, this will be adding this into the queue, and the queue will not be empty at any moment. And we all know that BFS stops as soon as the queue is empty. But if you keep adding those elements which are already visited, so the queue will never be empty, and you will get most likely you will get Stack Overflow error, or at least infinite loop. So these are the cells we can move to from this cell, right? But wait, in those cells there is also a target cell. As soon as you find the target cell, the coordinates of target cell you will already be having. It is, I guess, 1, 5, 1, 5. So from here 1, 5 is already reachable. That means you have found the minimum distance or minimum moves to reach here, and that would be distance of this plus 1. Distance of this cell is, I guess, 1. Yeah, distance of this cell is 1, so distance of this would be 2 because of the current cell plus 1, because from here it would require one move to go here. That is why the distance of this would be 2, and we would directly return from here. We would not continue, because we are not here to count the total number of or minimum distance of each node from here, each cell from here. We were only interested in finding the minimum distance from root or the starting position of the knight to the terminal position or the target position, and we have found it. So we will simply return from here the distance 2, distance of current node plus 1, which would be 2. So as you can see, using BFS we are able to calculate the minimum distance or minimum number of moves using which a knight will be able to reach its target position, and that would be 2 in this case. So this is how this algorithm works, and in the next lecture I'll be explaining the implementation of this algorithm. Implementation I'm not going to show in this lecture because this is already, I guess, too long. In the next lecture I'm going to take a problem from CodeChef, and then we'll be solving that problem, so you can also see the implementation in work. So if you look at the time complexity, it would be the same as the BFS on 2D grid, which is n cross m. So this was all for this lecture. Thank you guys for watching, and if you have any doubt or query, of course you can ask in the comment section or on the article that I've created for this course. So I'll be putting the link of that article in the description of this video. So thank you guys for watching. Until the next video drops, keep coding. Thank you.